Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this video is the next in our series about simple linear regression. In our last video, we talked about the very basics of regression. First, we discussed what residuals are, and then we learned about the sum of squares of those residuals. Lastly, we talked about how a regression model is actually a comparison to a special model where the independent variable does not even exist, and we just use the mean of the dependent variable. So in this video, we will talk about some of the nuts and bolts of regression. I will introduce some basic terminology and concepts that will carry you through your work using regression. We will talk about how regression is related to the algebra of lines, and discuss general patterns to look for on scatterplots. Now, there are no formulas or calculations in this video. The goal is to help better prepare you for interpreting regression analysis when it is performed. If you are new to regression or are still trying to figure out exactly what it even is, this video is for you. So, sit back, relax, and let's go ahead and get to work. So simple regression is part of a special area of statistics called bivariate statistics. And of course, bivariate means two variables. Now, in our previous videos, we talked about correlation, and we also talked about ANOVA. Now, if correlation and ANOVA got together and had a child, a very scary thought, I know, that child would be simple linear regression. Because regression shares traits with correlation, and it shares traits with ANOVA. Now, the sharing of all of those traits will become more apparent as we get further into regression. But for now, just kind of take my word for it. Now, correlation and regression also have something else in common, and that is that those data points are plotted on a scatter plot, or a coordinate plane. So for both correlation and regression, we have variable 1, and we have variable 2, and then we plot where each variable meets, and we get a data point. Now, of course, our samples will have more than one data point, so we'll populate it with some more points. Now, the relationship between variable 1 and variable 2 is special in this case dealing with regression. So we can say it like this. The value of one variable is a function of the other variable. So in this case, the value of variable 2 is a function of the value of variable 1. We could say it like this. The value of y is a function of x. So y equals f of x. So we will either choose randomly or be given a value for x. We will put that into some function, and then it will generate a value for y. But the value for y is always dependent on the value of x. So we can say it like this. The value of the dependent variable, in this case y, is a function of the independent variable, in this case the variable x. Now remember, in regression, the whole idea is to form a line through our data points that minimizes the residual sum of squares. But before we can really learn about that, we have to quickly review the basics of the algebra of lines. So I know you don't really want to go back to algebra, but you'd be surprised how many students I've worked with over the years that take stats their sophomore or junior year of college. They haven't had algebra in 5, 6, 7 years, and they forget some of this stuff. So just on one slide, I'm going to quickly review the algebra of lines. Now the most important thing to remember in this case is the slope-intercept form of a line, because that is basically how a regression line is stated. So remember that y equals mx plus b is the slope-intercept form of a line, and it's called that because it has two real components, the slope and the intercept. So x in this case is some random variable that we either choose or we are given in the problem. M in the slope-intercept form is the slope of the line this represents. You've also probably seen it written as rise over run. But x is the random variable and m is the slope. Now b is the y-intercept. It's where the line crosses the y-axis. So wherever our line is on this graph, wherever it crosses the y-axis, that is our y-intercept. Now the y-intercept has a couple of special properties. The y-intercept is where x equals 0. So if you think about all the points on the y-axis, they all sound like this. 0, 2, 0, 5, 0, 10, 0, negative 2, 0, negative 5, etc. So it's always where the value of x is 0. So every point on the y-axis looks like this, 0, comma, y. Now let's take an example. So we'll have this equation y equals 2x plus 3. Now look at that equation and then superimpose it on top of the slope-intercept form of a line. We can learn a lot about this equation. The first thing we can learn is that the slope is 2. So we have 2x plus 3. Over here on the left we have mx plus b. So 2 is where the m is, therefore the slope is 2. Now if we write it as a fraction, that's 2 over 1, because we don't write the 1 when we write whole numbers like that. So in terms of rise over run, it's 2 over 1. Now let's find the y-intercept. So we know that the y-intercept is wherever x is 0. So we can substitute 0 in for x and then calculate the value of y. So y equals 2 times 0 plus 3. So y equals 3. So we have the point of the intercept is the point 0, 3. So maybe it's about right there where the dot is. Now my graph here is not proportionally correct, so don't go off how the graph looks. Just sort of take into account what I'm writing on the graph. Now, of course, to graph a line, we have to have at least 2 points. Let's go ahead and figure out a second point, and luckily, this is easy to do. We can just pick any random value for x and then calculate y. So let's choose x equals 1. So we'll substitute 1 in where x is, and we'll go ahead and calculate the value of y. So 2 times 1 is 2 plus 3, so 2 plus 3 is 5. So the second point on our graph with a point 1, 5. Now we can go ahead and graph our line. Now remember, our slope was 2 over 1. So if this were graphed properly, we could go up 2 and over 1. Now remember, they're both positive, so 2 is upward and 1 is to the right because they're both positive. And we would end up at another point on our line. So this is a basic overview of the algebra of lines, because regression lines, when you actually do them in a stat software package, come out in this form. Now they don't come out in exactly that form, but they are related. So let's go ahead and show that relationship. So the slope-intercept is y equals mx plus b. Now the overall regression model for the entire population we are considering looks like this. Y equals beta sub 0 plus beta sub 1x plus e. So don't freak out. This is essentially the same thing you see over on the left. Now remember, as in many areas of stats, there is this very large overall population that we really don't know everything there is to know about it. because maybe we can't. So therefore we have to use sample data to estimate it. Now if we had the population available to us, this is what the regression model would look like. Now, how does it relate to over here on the left? So I color-coded it as well so you can see the relationship. So beta sub 0 is the y-intercept of the population parameter. So you can see on the left it's b, and over here on the right it's beta sub 0. Now beta sub 1 is the same thing as the slope of the population parameter. So beta sub 1 x over here on the right corresponds to mx over here on the left. And then e is the error term. In regression, it's the unexplained variation in our y variable. So I don't want to get ahead of myself here, but the beta sub 0 plus b beta sub 1 x will explain part of the variation, and then what's left will be error or unexplained variation. Now when we actually do simple linear regression, we write it like this. The expected value of y equals beta sub 0 plus beta sub 1 x. Now all you really need to know at this point is that this is pretty much the exact same thing as y equals mx plus b up here on the top left. So what is the expected value of y? Well, it's the mean or the expected value of y for a given value of x. So whatever x we choose or are given, the expected value of y is where we expect that to intersect in our graph. Now again, this will become more apparent as we go, but this is how we actually write the simple regression model. Now the expected value is the mean. So what does that actually, well, mean? So if we have a coordinate plane here where we have x and y axis, and we pick a value for x, so maybe here sort of in the middle, well that corresponds to a value of y, and that's our data point, maybe right here. But that's the expected value of y. It's really not that simple. There's actually a distribution of y's for that given x. So remember, our regression model is not going to be perfect. So any expected value of y we come up with is at best going to be an approximation. So when we say the expected value, what we mean is that it's the mean of a small distribution for that y. So it can be fairly narrow, like this. You can see that our distribution of y's falls in a narrow band. Or it can be the exact same point. So this exact same point, with the expected value of y's can be much wider, like that. Now obviously in regression, we want to have the situation like is over here on the left. So we want to have the expected value of our y's to be in a sort of a narrower range, a narrow distribution, than we do over here on the right. But just remember, the expected value of y is really the mean of a distribution of those y values. Now this will become more important as we get into more complex topics about regression, but I just want to point out that the value of y isn't really a point. It's the mean of a distribution around the y's. Now regression lines can take three general forms. So here we have our expression up here on the left, or our equation up here on the left. So expected value of y equals beta sub 0 plus beta sub 1 times x. So we can have the first case. So it looks like this. The expected value of y equals beta sub 0 plus 0 times x. Well, what is the 0 in this case? Well, that's where the beta sub 1 is. So what is that saying? Well, that's saying that the slope is 0. But if we go ahead and multiply this out, we end up with just expected value of y equals beta sub 0, because everything to the right of that is 0 because of the multiplication. So on our graph, if our slope is 0, it looks like this. The line is flat. That is a line with a slope of 0. So the slope, b sub 1 or beta sub 1, is 0. Now the second type might look like this. expected value of y equals beta sub 0 plus beta sub 1 x. Now notice that the slope, the beta sub 1, is positive. So it looked like this. So the slope, beta sub 1, is a positive. So our line goes from the lower left upward to the right. Now the other general type looks like this. The expected value of y equals beta sub 0 minus beta sub 1 times x. In this case, our slope, the beta sub 1, is negative. So it might look like this, where our line goes from the top left down to the lower right. So again, these are general patterns that are based on the sign and the value of beta sub 1, because beta sub 1 is the same thing as the slope. So mx plus b, this is beta sub 1 times x. Beta sub 1 is the slope. So our lines might sort of form a general pattern based on the value of beta sub 1. So if we actually knew the population parameters, beta sub 0 and beta sub 1, we could use the simple linear regression equation that looks like this that we already saw. But in reality, we almost never have the population parameters. Therefore, we will estimate them using sample data. When using sample data, we have to change our equation a little bit. It looks like this. Now, the y with the little thing on top, it's pronounced y hat. And it is the point estimator of the expected value of y. So y hat is the mean value of y for a given value of x. So just like other cases in stats where we're using sample data, we write the equations a bit differently. So all we do is use lowercase b where we have the betas in the top equation. And of course we have y hat versus the expected value of y. Now in functional terms, they act the same way. We just write it this way to acknowledge that we are using sample data. So here is our same graph, but now we write it with y hat. So in this case, we're using sample data, but the basic idea is the same. So y hat is the mean of the expected values of y for any given value of x. Otherwise, it's the exact same concept. So let's look at this in the context of a problem. Now this data, or this graph, is from our first video where we had the dollar amount of tips, like a waiter or waitress received in a restaurant, but we didn't have the matching amount of the actual bill. So all we had was the tip amount. We only had the one variable. We only had the dependent variable at that. So the best we could do is make a graph based on the mean of the tip data, which was $10. So then we went through and found the residuals and squared those and then added them up. So we had the sum of squared errors, or squared residuals, of 120. So in this case, what's the slope of this line? Well, it's 0, because the independent variable doesn't even exist. So the slope of this line is 0 because we're only using the values of the dependent variable. So when conducting simple linear regression with two variables, we will determine how good the regression line fits the data by comparing it to this type, where we pretend the second variable does not even exist. So we covered that in the previous video. But the important thing to apply in this video is that the slope of this example, the slope of this special type of situation, is 0. So this is when beta sub 1 is 0. So any regression line we come up with, we will always be comparing it to the situation where the slope is 0. And the most extreme case where the slope is 0 is where the dependent variable is where the independent variable does not even exist. So in this situation, the value of y hat is 10 for every value of x. So we can actually do this algebraically. So y hat equals b sub 0 plus b sub 1 times x, but the slope is 0, so we insert that in where b sub 1 is. So we're left with y hat equals b sub 0. Well, what is b sub 0? Well, it's 10. So y hat equals 10 for every point along the x-axis. So for the second tip, it's $10. For the fifth tip, it's $10. For the fourth tip, it was $10. So we're always comparing our regression model to this example where beta sub 1 is 0, or the slope is 0. So let's go ahead and do a quick exercise where we can match an equation with the general regression model. So we have an equation that's y hat equals 0.3 minus 3.3x. Then we have y hat equals 48 plus 7.8x. And then y hat equals 14.87 minus 0.014x. Then we have our three general forms. So in our first example, our slope, beta sub 1, is at or near 0. In the second example, our slope is positive, so beta sub 1 is positive. And in our last one, beta sub 1 is negative. So let's go back up to our first equation. What is the value of the slope in our first equation? Well, it's negative 3.3. So it's negative. So which one does that go with? That general shape. So if we graph this equation, it probably looks something like the bottom right. Now what about our second equation? What is the slope there? Well, it's positive 7.8x. So it would look maybe like the second example here at the bottom. Now what about our third one? Our slope is negative 0.014. Well, that's very, very close to 0. It's not exactly 0, but it's close. So if we graph that line, it would probably look something like that. So again, depending on the value or the sign of the slope, we can have a general idea what the regression line will look like. Let's go ahead and get ready for conducting the least squares, which we will do in the next video. Now remember, in the first video in regression, we only had the dollar amount of the tip that the waiters or waitresses received. We didn't have the meal amount. So now we're going to go ahead and add that in. So for the bill of $34, I had a tip of $5. For a bill of $108, I had a tip of $17, and so on and so forth. Now when we go ahead and graph those on a scatter plot, it looks like this over here on the left. So you can see where each data point falls with relationship to the bill amount and the tip amount. Now remember, what we're saying here is that the tip dollar amount depends on the original bill amount. That's what we think. That's what we're sort of hypothesizing. So in general, a lower bill will result in a lower tip, and a more expensive bill will result in a higher tip. That's sort of our hypothesis. So if we graph these on the scatter plot, we can look and it appears that there's some sort of linear relationship that goes from left to right. So if we drew a line, it would probably start at the lower left and go to the upper right. And most importantly, if that line reduces the residual sum of squares significantly from the model where we only use the mean of the tips of $10, then that's when we will say that a regression model is good, sort of in a qualitative sense. Now quantitatively, we'll be able to figure that out more concretely, but generally, if the residual sum of squares is a lot less using our regression line we come up with using the least squares method, then we'll know that our regression line is much better than the example where we only use the mean tip amount. Okay, so that wraps up our second video in our linear regression series. And again, here I wanted to review a couple of things. Sort of the algebra of regression lines, some general model equations that you will see going forward and you will see in your own work, and then some general graph patterns that you can look at the equation and try to figure out what the graph means and vice versa. So again, this just sort of lays the groundwork for the actual calculations that will start in the next video, where we will actually calculate the least squares method and figure out our regression line by hand.